Hey guys, so here is a complete run through of angular motion for OCR and AQA A-level PE. So firstly, they expect you to be able to define angular motion. So angular motion is the movement of a body in a circular path around an axis of rotation. And there's three axes of rotation that they want you to know about. So there's an axis of rotation that runs through the body from front to back, and that's called the frontal axis if you're an OCR student. And then they call this one the sagittal axis if you're an AQA student. And this is where you could perform a cartwheel. So these are just imaginary lines that you'd be rotating around. The next axis of rotation is the transverse axis that runs from left to right. And around this axis of rotation, you'd be performing a somersault. And then the final axis of rotation is the longitudinal axis. And I always remember that this is the longest axis in the body. And this is where you'd be performing a pirouette around. Now, all of those movements are examples of angular motion because they are all the movement of a body in a circular path around an axis of rotation. They'd also expect you to be able to outline how is angular motion created. So let's say that this is a football and this is the centre of mass of the football. You can either apply a force that goes through the centre of mass, or you can apply a force that goes outside the centre of mass. And this is the type of force that would cause the football to spin more. And therefore, this is the type of force that would create angular motion. And this is known as an eccentric force. So an eccentric force is just an external force that passes outside the centre of mass of an object. So that's what angular motion is, examples of angular motion and how it's created via eccentric forces. They then want you to be aware of something called the conservation of angular momentum. And this is a really important equation to know. So angular momentum is moment of inertia times angular velocity. So let's break those three terms down first. So angular momentum, that is the quantity of angular motion a body possesses. So a really generic definition there, but it's just how much angular motion something has. And it's made up of two things, moment of inertia and angular velocity. Now, if something's travelling at a fast velocity, it just means it's travelling quick. And then if you just put angular in front of that, it just means that it's spinning quick. So angular velocity is the rate of rotation. It's just how quickly is something spinning. And we measure that rate of spin in radians per second. So angular velocity is measured in radians per second. And radians, they're a bit like degrees. They're not exactly degrees, but radians is just measuring the amount of rotation that has happened and then over a given amount of time. So angular velocity is the rate of rotation. If something's travelling at high angular velocity, it will be spinning really quickly, and that's measured in radians per second. And then moment of inertia, this is the resistance a body has to a change in its angular motion. And what that means is if something isn't currently spinning, it'll have a resistance to being spun. Or if it's already spinning, let's say at 10 radians per second, it'll want to continue at that rate. It won't want to speed up or slow down. A moment of inertia depends on two things. It depends on the mass of the body, which is measured in kg, and then the distribution of the mass around the axis of rotation. And what we mean by that, let's say we're looking at this ice skater performing a pirouette. They'd be doing that around the longitudinal axis. And they can either distribute their mass further away from that axis of rotation, or they can distribute the mass closer to the axis of rotation. And we measure that distribution of the mass around the axis of rotation in meters squared. So overall, because moment of inertia depends on both the mass and the distribution of the mass around the axis of rotation, you'd have to say that bit to get the mark. Because it depends on those two things, moment of inertia is measured in kg meters squared. And then because this is a times equation, you bring these two units of measurement together. So angular momentum is measured in kg meters squared, radians per second. So you just join those two units together. Now, in an explain question, what they'd expect you to outline is how can an athlete alter their moment of inertia, and then what impact would that have on their angular velocity? So moment of inertia and angular velocity are inversely proportional to each other. So if moment of inertia decreases, angular velocity will increase, and that's known as them being inversely proportional. So we'll write inversely proportional there. And they'd expect you to be able to outline how does the athlete alter their moment of inertia, and then what impact does that have on their angular velocity. So if we go back to the two factors affecting moment of inertia, you've got the mass and the distribution of the mass around the axis of rotation. And in a given moment, an athlete would only be able to change the distribution of their mass. They wouldn't be able to change their mass. So they can either distribute their mass further away from an axis of rotation or closer to it. And when they distribute their mass further away from an axis of rotation, we say that that increases their inertia. So now in this position here, they're more resistant to spin. And as a result of that, that decreases their rate of spin. So that lowers their angular velocity. So here they've distributed their mass further away from the axis of rotation, which has increased their inertia and lowered their angular velocity. Whereas in this scenario, when they've distributed their mass closer to the axis of rotation, this will lower their moment of inertia. So now in this scenario, they are less resistant to spin, and that allows them to then spin quicker. So their angular velocity goes up in this scenario here. Now, in between those 2 points, we would say that the angular momentum has remained the same. It's conserved. And that's where the name of this topic comes from, the conservation of angular momentum. Angular momentum is conserved throughout a movement because the two things that make up angular momentum are inversely proportional to each other. So if one increases, the other decreases, and therefore angular momentum doesn't change. And sometimes they will illustrate this on a graph where you've got angular momentum being this top line, because this just remains the same throughout. And then moment of inertia and angular velocity will look like this. And often they'll have a diagram of a person above, and they'll want you to work out which line is which. So we'll come on to that later. But that is the conservation of angular momentum. In terms of working out angular velocity, it's the same as normal velocity. So you just do angular displacement divided by time. And the subtle difference between angular distance and angular displacement. Angular distance would be the total change in angle, so the 360 plus the 90, whereas the angular displacement would be the smallest change in angle, so just the 90 degrees. And then the final topic that they want you to be aware of is being able to adapt Newton's laws to angular motion instead. So what I've done so far is I've written out each one of Newton's laws, but I haven't adapted it to angular motion. So Newton's first law of inertia is basically just saying something remains still until you hit it. So it says a body will continue at rest or at constant velocity unless acted upon by an external force. So the way that we'd subtly change this is we'd say that a body will continue at rest or rotating at constant angular velocity unless acted upon by an external torque. And a torque and an eccentric force are the same thing. So this eccentric force here, you could also call that a torque. So basically every time that you mention, just put E there, every time that you mention the word force, you just replace it with torque. So now this reads, a body will continue at rest or rotating at a constant angular velocity unless it's acted upon by an external torque. So for example, the ice skater will continue spinning at a constant angular velocity until they apply an external torque to the ice to speed up or slow down. Newton's second law of acceleration is basically saying how hard you hit something determines how quickly it travels. So it says the acceleration of an object is directly proportional to the size and the direction of the force applied. So to adapt this now for angular motion, we just put the angular acceleration of an object is directly proportional to the size and the direction of the torque applied. So what this means is, if we go back to that diagram earlier, the greater the torque the footballer applies to the ball, the greater the angular acceleration of the ball. So the harder you hit the ball on the side, the quicker it will spin. So that is Newton's second law of acceleration applied to angular motion. And finally, Newton's third law of action-reaction normally states that for every action force, there's an equal but opposite reaction force. So all we have to do here is say, for every action torque, there is an equal but opposite reaction torque. And you can pretty much apply this the same way as you would have done for linear motion. So you could say that the ice skater applies an action torque downwards into the ice, and the ice applies an equal but opposite reaction torque upwards on the ice skater, causing them to rotate into the air. So that is everything on angular motion. And if you've got any questions on that, leave them in the comments. Also in the comments, let me know if there's any other topics that you'd like me to do these run-throughs for, and check out the link in my bio for access to free resources, past paper question booklets where you'll want to apply all of this knowledge to.